Dear all, welcome to EEE570 lecture today. Today I want to begin with mutually coupled branches in Y-bus. If you remember, so far we have discussed how Y-bus is formed, and I showed you two different methods when constructing bus admittance matrix Y-bus. Today I want to continue with the mutually coupled transmission lines or branches and how they are included in the formation of Y-bus. Yes, first we draw two branches which are mutually coupled with each other. These are the bus names MN, PQ. These boxes represents the impedance of each branch, ZA, ZB, and this notation shows that there is a magnetic coupling between these two transmission lines, and Zm with this respect is called mutual impedance between these two branches. So Za is the self impedance of the upper line, Zb is the impedance of the lower transmission line, while Zm is the mutual impedance between these two transmission lines. If IA is the and IB is the transmission line currents, and also if plus minus VA is the voltage drop of the upper transmission line, while plus minus dB is the voltage drop on the second transmission line, we can write these voltage drop equations in matrix form. That will be like this: VA VB is equal to ZA ZM ZM ZB and the current vector IA IB. How this equation is constructed, let me write the first row equation. VA is equal to ZAIA plus ZMI, and from here you can see that the first component ZAIA is the voltage drop due to the self impedance of the first upper transmission line, while ZMIB is the voltage drop term due to the second transmission line, by considering mutual impedance Zm. While there is a plus sign here, it is related with the dot locations. If you look at the figure, these two currents, IA and IB, are entering from these two dots on both transmission lines. So as a result, there must be a plus sign here. For example, if the dot position on the second transmission line is here, at the opposite location, for example here, then this sign must be negative. After writing this matrix equation, since this is a square matrix, we can find its inverse. Since this is the impedance matrix, because this is the voltage vector and that's the current vector, so this is our impedance matrix of this small transmission system. So if we find the inverse of this square matrix, we can find the bus admittance matrix of this small power system. Okay, let's write the inverse of this square matrix ZA, ZN, Zm, Ze inverse will be equal to Ya, Ym, Yb. Since the impedance of since the inverse of an impedance matrix will be equal to the a corresponding admittance matrix. If we take the inverse of this 2 by 2 matrix, we will find that 1 over Za Zb minus Zm square multiplied by Zb minus Zm minus Zm Za. Yes, this is a fast way to calculate the inverse of a 2 by 2 matrix. And that will be equal to Ya, Ym, Yb. And if you want to put this admittance matrix in another equation involving voltage vectors and the current vectors, we can write such an equation. Okay, let's write Ya, Ym, Yb multiplied by voltage drop vector as Va, Vb is equal to Ia, Ib, which is the current vector of the system. You can see that this admittance matrix is the multiplication of the voltage vector, and after this multiplication you can reach the current vector of the transmission system. This matrix has a name which is called as primitive admittance matrix. While the previously found impedance matrix is called primitive impedance matrix. So, okay, let's write again. Za, Zm, Zm, Ze is called primitive impedance matrix. So we can say that the inverse of primitive impedance matrix is equal to primitive admittance matrix, or vice versa. So as you see, they are reciprocal of each other. Now, if we want to write each term of primitive admittance matrix separately, we can write Ya is equal to Zb over Za Zb minus Zm square, and similarly Ym will be equal to minus Zm over Za Zb minus Zm square. We also discover that Ya and Yb are, except the numerators, yes, except the numerators, they are equal to each other. So let me write YB is equal to ZA over the common denominator as ZA ZB minus ZM square. So up to now we have discussed that primitive impedance matrix, the definition of primitive impedance matrix as well as the definition of the primitive admittance matrix, and we see that if one of them is inversed, we find the other one. I mean, they are reciprocal of each other, and each element of the primitive admittance matrix can be written in terms of the elements of primitive impedance matrix. By you can check this situation with these last three equations. Yes, these equations. After some derivations, and these derivations are in your notes, we have studied to derive these equations in the last hour. If you remember, you can check your lecture notes. For the same system, I mean, for the same these two transmission line, we can write. Finally, we can write this matrix equation and this will be the voltage vector Vm, Vn, Vp, Vq, and that will be the current vector Im, In, Ip, and Iq. But what are these voltage and the current terms? Okay, let me provide this figure. These are bus names M, P, N, and Q. These are branch currents IA, IB. These are branch admittances YA, YB, and that's the mutual admittance between these two lines as YM. We know that how YA, YB, and YM is calculated. You can refer to these equations that we derived so far. What else? Let me show you externally injected currents to these buses. This is IM. That's IP. That's IQ. And that's IM. Yes, we clearly see that external injected currents and branch currents can be written in terms of each other. With this respect, on this figure, there are 6 different types of currents, and as you see here, that's my current vector as IM, IN, IP, IQ. VM, VN, VP, VQ are the bus voltages as VM, VP, VN, and VQ. The left side square matrix, as you see, involves many parameters, and these parameters consist of YA, I mean the combination of YA, YB, and YM. In order to understand the concept more easily, we can give some extra information for this large square matrix. Okay, let me write M N P Q and same M N P Q. Okay, what I did here, just I write the names of the buses as rows, as a row information and as a column information, as you see in my last step. But what is the meaning of these codes? In order to understand the meaning of this last step, we have to compare this large admittance matrix with this figure. For example, I want to make a little square matrix in this large admittance matrix. So as you see, this little square matrix has a dimension of 2 by 2 and it involves only the component YA. As you see, we have YA and minus YA. And if you look at the related row and the columns, you see YA and minus YA is only available between bus M and bus N. If we return to the figure, yes, that's actually true, because as we see, admittance YA is only between bus M and bus N. When we come to here, for example, I want to draw another 2 by 2 matrix, and as you see, this matrix consists of only YB and minus YB. If we come to this figure, YB, which is located here, is replaced between bus P and bus Q. And if we check the row names, you see these are the row names as PQ, and these are the column names as PQ. You see YB is replaced between bus P and bus Q. So this square matrix as a kind of visual verification by using this figure. What about YM, mutual admittance, which is written here? Yes. As you see, we can draw another 2 by 2 square matrix like this. And let's see what are the bus names and what are the bus names in the rows and in the columns. You see, as a row name, we have P and Q, but as a column name, we have P and Q, but as a row name, we have only M and N. So let's try to set up a relationship between this notation and this figure. I see that Ym is the mutual admittance between these two transmission lines, so it is related, it must be related with these four buses, because these four buses are the endpoints of these two transmission lines. Because of this, bus names, all the bus names, I mean M and PQ, must be written in order to describe the row names and the column names when constructing this matrix involving the term Ym and minus Ym. What about this 2 by 2 square matrix? Again, it consists only of Ym and minus Ym, and if we check the related row and the column names, we see that Mn are the column names, while P and Q are the related row names. Again, we see that Ym is replaced between these two transmission lines, and these two transmission lines in total are connected to four buses which are named as M and P and Q. So you see, we can see M and PQ all are written, all bus names are written in order to describe row names and the column names. So if we have a two parallel transmission line, and if there is a mutual admittance between these two transmission lines, the respective admittance matrix will be 4 by 4. As you see how the dimension of the admittance matrix is increased by the inclusion of mutual admittance. There is also another important point why P is written before Q, and another important question why M is written before N when giving codes to the rows and the columns. The answer is here. If you check the figure, look at the dot locations. One dot is here, another dot is here. You see this dot is near bus M, and this dot is near bus P. So when describing which letters must be written first, we have to check the dot locations of the mutual admittance, and we should write the names of the buses first, in which the location of these two, the location of the dots is the most near to the respective bus. Here, this dot is near bus M, so M is written before bus N. Hence, M and M will be written before M. When we come here, this dot is near bus P, and hence P must be written before Q, so you have to write always PQ, PQ. And here you have to always write M and M. So here we discover that how the dot locations of the ym is used when constructing this overall admittance matrix. When I come to this square matrix, let me mark. You see this square matrix can be written also like this: 1 minus 1 minus 1 1. You see, because ya is the constant multiplication term. And similarly, we can also write 1 minus 1 minus 1 1 for the ym as well, and we can also write 1 minus 1 minus 1 1 yb and 1 minus 1 minus 1 1 for ym. You see, this previously found admittance matrix can also be written like this in this new form. Here we are using a common square matrix involving only plus 1 and minus 1, and these are the multiplication coefficients of each 2 by 2 square matrix as ya, yb, ym, and ym. And we give the name to this matrix as nodal admittance matrix of the system. Nodal admittance matrix. Let's continue with example on page 43. In this example, we have 3 buses and 2 transmission lines. This is bus 3. This is the first transmission line, which connects bus 3 and bus 2. And that's the other transmission line, which connects bus 3 and bus 1. J 0.25 is the impedance of the first transmission line, while the same J 0.25 is the impedance of the second transmission line. We note that these are in per unit quantities, and these numbers represent line impedance. What about mutual impedance? The mutual impedance information is given like this. These are the dot locations, and mutual impedance between these two transmission lines is given as 0.15. So Zm, we can write the mutual impedance between these two transmission lines is Zm is equal to J 0.15 per unit. While Za and Zb are equal, and they are J 0.25 per unit. So this is the description of this little power system involving 3 buses and 2 transmission lines. The question is, find the nodal admittance matrix for mutually coupled branches and write corresponding nodal admittance equations. Yes, Y bus is our question. What is the nodal admittance matrix of the system? At first, we have to find the corresponding admittance values YA. What is YA? If we come here, you see this is the equation necessary in order to find YA. So YA is written like this: ZB over ZA ZB minus ZM square. And we know ZB is equal to J 0.25 divided by J 0.25 squared minus Zm squared J 0.15 squared. So the answer is minus J 6.25 per unit. Similarly, we can find Ym, which is the mutual admittance of the system. Again, I am coming here. We previously find that Ym is equal to this equation. So Ym will be written as minus Zm over Za Zb minus Zm square. If we substitute the values, minus J 0.15 over J 0.25 squared minus J 0.15 squared, and the answer will be found as J 3.75 per unit. Note that Yn and Yb are equal. You see, Yn and Yb are equal parameters. Sorry, they are not equal. Yes, for this example, they are equal because Za is equal to Zb. So I can write Ya is equal to Yb because of the fact that in this example, Za is equal to Zb. So we find, up to now, we find Ya, Yb, and Ym. This is Ya, also Yb, and Ym. Now the next step will be constructing Y bus by using the method previously. Look at the second transmission line. You see the second transmission line is connected between bus 3 and bus 1, and we know the admittance of this line as Ya. So we need to combine these bus names, I mean 3, 1 with Ya. So let me write 3 minus 1 minus 1 minus 1 1. So this is our square matrix. I mean, it's a kind of unit. It's a kind of unit square matrix in this solution method, and the multiplication factor will be YA. And what is YA? YA, yes, as you see, YA is found as minus J 6.25. This squared matrix is completed, but we have to show the names of rows and the columns since this second transmission line here is connected between bus 3 and bus 1. Since the dot location is here, we have to write first 3 and then second 1. So 3 1 3 1. Yes, as you see, the first elements of the Y bus are completed. What about the other transmission line? If I separate the region like this, yes, you see other transmission line is here, which is replaced between bus 3 and bus 2. And also we see that you see the dot location is near bus 3 rather than 2. So we have to write 3 2 3 2. 1 minus 1 minus 1 1. And then we need to write minus J 6.25, which is equal to YB. And the rows and the columns names must be written like this: 3 2 and yes 3 2. Yes, the self-admittance components are completed like this. What about mutual admittance components will be replaced in this Y bus? Again, I am writing the unity squared matrix 1 minus 1 minus 1 1. What is Ym? You see Ym is found as J 3.75. 3.75 is our multiplication constant. Yes, the critical question is what must be the names of rows and the columns. You see the mutual effect is between these two transmission lines, and we have two dots as located like this. You see the first dot is near bus 3, and the second dot is also near bus 3. So we have to write 3 2 and 3 1. 3 2 3 1. So 3 2 3 1. And also, in order to fill this empty region in this Y bus, because this is the Y bus of my overall system, again we are writing 1 minus 1 minus 1 1, which is multiplied by Ym J 3.75. Now, what must be the names of the related rows and the columns? We are just making a transpose. I mean, if the rows are written like this, 3 1, 3 1 must be written like this. Just we are transposing. Okay, yes, we are making a transpose. 3 1 is written like this. 3 2 will be written like this. So you see, the column names are replaced with the row names and vice versa. As you see, we have 4 by 4, a total of 16 parameters, and these 16 parameters must be calculated. For example, what is this value? This value is 1 multiplied by minus j 6.25. For example, what is this element? What is the magnitude of this element? I mean, 2 and 3. You just multiply minus 1 by minus j 6.25 and vice versa. And as you see, you have to compute this, you have to repeat these steps 16 times. But at the end, what must be the dimension of Y bus? If you check all of these matrices together, you see the maximum number of rows is 3, and the maximum number of column is also 3. So the Y bus dimension will be 3 by 3. So you have to clarify 9 elements which must be replaced in this squared matrix. But the question, how can we find these 9 elements? It is not very difficult. You just look at the row number and the respective column number, and you are making grouping. For example, in order to write Y bus first row, first column, you have to combine these elements. For example, this, because for this element, the row and the column number is 1 and 1. Also, I am searching any similar entry, 1, 1. As you see, I don't see any further elements whose row and the column number are at the same time equal to 1. So Y bus 1, Y bus 1 and 1 must be minus J 6.25. What about Y bus 1, 2? This is our second element in Y bus. 1, 2 means that we are at the first row, but column is 2. So yes, we are searching all the entries whose row number is 1 but column number is 2. Is there any such element? Yes, I found an entry like here. Here you see the row number is 1 and the column number is 2. So Y bus 1, 2 will be J 3.75. Okay, let's write J 3.75. What about Y bus 1, 3? Now we need to search all the entries whose row number is 1 while the column number is 3. I am searching for 1, 3. Yes, I found an entry like this, 1, 3. This. Okay, let me use square shape. You see row number is 1 and column number is 3. Is there any such element having the same properties? Yes, I also see this entry. You see minus 1 multiplied by this number. Here also I check that row number is 1 and the column number is 3. Since there are two entries, we must add these two numbers. You see minus 1 will be multiplied by minus j 6.25 here, so the answer is j 6.25. And here minus 1 must be multiplied by j 3.75, so I have to write minus j 3.75. And as you see, the answer will be j 2.50. j 2.50 is the answer. As a first time, I did something not common, because in my larger matrix structure, I found that there is more than one entries whose row number is 1 and the column number is 3. So as a result, we are making a superposition, and we are adding all the entries having the same row number and the same column numbers. So as a result, ybus13 is found as j2.50. You see, we completed the first row of ybus. What about second row? ybus 2 and 1, I mean second row, first column, 2, 1. Okay, let's check. Is there any entry whose row number is 2 and the column number is 1? Yes, I see such an entry. You see, row number is 2 while the column number is 1. So the answer will be 1 multiplied by j 3.75. So I am writing the result here. j 3.75 per unit. What about ybus 2, 2? Now we are searching all possible entries whose column and row number is equal to 2. So in simply, we are searching for all the entries like 2, 2. So I see only one entry here. You see row number is 2 and column number is 2 as well. So the answer is minus j 6.25. What about ybus 2, 3? 2, 3. Yes, I see more than 1, 2, 3 entry. This is the first one. And that's the second one. So minus j 3.75 plus j 6.25, and the answer is j 2.50. Second row of ybus is completed. What about third row? ybus 3, 1. The row number will be 3 and the column number will be 1. Yes, 3, 1 is here. It corresponds to j 6.25. Is there any other entry? 3, 1. 3, 1, yes, it is here. 3, 1 is here. So minus j 3.75. The answer will be j 2.50. What about Y bus 32? 32 is here. One of the entry is here. Minus J 3.75. Another 32. Yes, I see here 6 because minus minus plus. J 6.25. And the answer is again 2.50. What about Y bus 33? Yes, I am searching all the possible entries whose row and the column number are all three. Yes, as you see, I have four entries. One of them is this minus J 6.25. This is my second entry, J 3.75. Another entry is here, J 3.75. And last entry is here, minus J 6.25. And after the addition, we can say that the result is minus J5. Yes. Minus J5 per unit. So all 9 elements are completed in Y bus. Okay, let me write them in matrix form. Y bus 1 is written here, minus J 6.25, J 3.75, J 2.50, J 3.75, minus J 6, sorry, minus J 6.25, J 2.50, J 2.50, J 2.50, and finally minus J 5. So this is the nodal admittance matrix of this power system having 2 transmission lines and 3 buses. The dimension is, as you see, 3 by 3. As you see, the addition of Mutual effect between these transmission lines increases the size of the Y bus, because if Mutual effect is ignored, I mean if Ym is simply 0, then the dimension of the Y bus will be 2 by 2, which is just equal to the bus number. So you see how Ym affects when constructing Y bus. Let me remind you how this Y bus can be used in our calculations. Y bus matrix will be written like this: Y bus multiplied by bus voltage vector will be equal to injected current vector to each bus. So in this equation, if we know injected current vectors, and after the calculation of Y bus, you can find bus voltage vector V1, V2, and V3 can be easily calculated. Yes, there is a correction from my side. I have to say this. The Moschel effect does not increase the size of the Y bus because if Moschel effect is fully ignored, since there are three buses in this example, one, two, three, Y bus, the size of the Y bus will be three. After the addition of Moschel effect, the size of the Y bus doesn't change. So there must be a correction like this. So the size of the Y bus is only changed by addition or removing any bus. This is very important. So the Moschel effect does not affect the size of the Y bus. Okay, up to here, we have discussed both considering my lecture notes with this online distance video. So far, we have discussed how a Y bus of a power system is constructed. In both cases, I mean with or without Moschel effect. With Moschel effect, yes, there are some additional computations, but the method is rather straightforward, and I think it's not so difficult. You can apply this method easily into your problems. Uh, and we have seen that the addition of Moschel effect into the transmission lines does not increase or decrease the size of the Y bus. Just the calculation steps uh, are becoming different. Uh, and yes, we are coming an end here to an end here, and thank you for listening.